All right, so in this particular example, we are going to be doing some conceptual thinking about what's going on when you're looking at a curve. And this is the curve that we're going to use to talk through this. So the issue is that by just looking at the curve, you should have some type of an idea of what type of titration is occurring here. And that would actually correlate pretty well to the next slide. And the next slide says, you know, what kind of titration is featured in the curve on the previous slide. So what type of titration is featured in that curve? Yes, it is a weak acid. Strong base. And the general reaction for the type of titration that we chose, the weak acid strong base, might be something like this. HA would be like some type of an acid. Plus a strong base, so it'd be like OH minus, would react to form something like the conjugate of a weak acid and water. Now, the issue is that, I guess in terms of like quantifying that, you have to understand that we have CH3, COOH, that would be our weak acid. Strong base would be something like NaOH. Would make something like the conjugate, which is the acetate ion, which would be something like CH3COO minus plus Na plus water here. So, and again, the Na doesn't do anything. It's kind of inconsequential. So we really wouldn't have it at all. But again, or not again, but the thing of it is that generally speaking, if the sodium hydroxide is the limiting reactant, right, it gets all used up, at some point you are going to have a small amount of the original weak acid, and you're going to potentially have a larger amount of the conjugate base of the weak acid. So this type of problem might go into a KB problem, because you're going to be looking at calculating something about the pH maybe of the conjugate base. Now, looking back at the curve that we were looking at, it says label the buffer region on the titration curve. Where would you identify the buffer region to be located about? Yeah, it'd be in the range of A to C. It also asks you to identify the equivalence point on the titration curve. And where would you find the equivalence point here? What? D. What is true at the equivalence point? Moles of acid equals moles of base. Okay, any questions about these first four? No? Okay. Looking at this curve, it says, what is the pKa of a weak acid? So, in this case, when we were looking at the curve, actually, where would you identify the point to be the pKa? It would be at B. So if you're kind of eyeballing the curve, what would the pKa value be?
Like just above 4.
It'd be just about above 4. So I don't know, somewhere between 4 and like 4.4 maybe. So the issue that you have to remember is that the reason why the pKa of a weak acid is equal to the pH is because the concentration of the weak acid is equal to the concentration of the conjugate base at the half equivalence point. And according to the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the concentration of the conjugate over the concentration of the weak acid. And in this case, if they're equal to one another, they give you a value of 1, and the log of 1 is 0. So that's how we know that the pH and pKa are equal at that point. Now, question 7, read it, or question 6 rather, read it very carefully because it is worded a little trickily. At what point is the concentration of the weak acid approximately half of the concentration of the conjugate? I'm going to say that it's C. Think about it. As you are going from left to right across the graph, you're adding more NaOH. The NaOH is getting eaten up by the weak acid. The weak acid is getting used up and producing conjugate. So the conjugate base is going to be in greater concentration as you get to the right side of the buffer zone, right? So we could make the assumption that as we get closer to C, the conjugate, the concentration of the weak acid is less than the concentration of the conjugate base. Number 7 says at what point is the weak acid equal to the conjugate base? We've already kind of identified that as point B. And at what point would the hydroxide be the majority species? D. I would say it's a better bet would be E, but you might want to say anything. Might want to make the statement anything or any time after E or after D. Wow, words. AFTER after D. Okay, so I did tell you last night to start working on these. I'm going to assume the vast majority of you did not. I said the vast majority. I didn't say Megan did not. But I'm sure that's what you heard. Now, so here's the thing. This is not going to be a super major focus of the AP exam, but I do believe that you should be aware of a titration curve for a weak polyprotic acid. Remember, polyprotic is anything that has more than one proton, so it would be an acid that has like H2 or H3 as part of it, okay? So in this particular scenario, we are using the weak acid H2SO3, which is sulfurous acid, and we are adding strong base to it, so it's a weak acid strong base, but it's polyprotic because we have two hydrogens that can be pulled off here. Now, couple of things. In this particular reaction, what makes this different is the fact that we have a buffer region, an initial buffer region, we have a secondary buffer region, and then we have the secondary equivalence point, and then the curve levels off. So in this particular case, we are starting with an acid that has a pH less than 2, and it's moving forward, and somewhere around 1.85, its pKa is equal to is equal to like the pH. Now, in this particular region right here, okay, this would be the half equivalence point for the first deprotonation. So what's happening is we are taking the H2SO3 and we are removing one hydrogen from it and being left with HSO3 minus. So at the half equivalence point, we've done half of that, or well, the concentrations of those are equal. And we get to the first equivalence point, so right here, I'm telling you that the pH is 4.25, but at that point, moles of the H2SO3 would equal moles of the NaOH. Okay? Now at some point from here to here, okay, so some point from here to here, we remove all of the primary hydrogens. We remove all of the one hydrogen. and you get to entering into the buffer zone, in which case you will have this reaction that you have to take or consider, in which case it will deprotonate to H plus and SO3 minus 2. Okay? So at this point, we now have a new buffer region. We have a new half equivalence point. Okay? And the new half equivalence point has a new pKa/pH of 7.19. Still not neutral, just beyond neutral. And so at this point, we are in a situation where that's our half equivalence point. But then when we get to the actual secondary equivalence point right here, this is when moles of HSO3 minus equal moles of NaOH. And once at some point over here, it is completely deprotonated, and our primary species would be OH minus. Does that make some type of sense? Yes, no? We good? Move forward? Anybody want to laugh? Yeah.
Is that in the middle of the second buffer region?
Yes.
Okay.
Yes, ma'am.
I have a question about
Okay. Now this guy here, we can use pKa values to make judgments about the protonation state of a multiprotonated acid. So glycine is an amino acid. It's a fun amino acid. It's useful for a lot of things in the body, like glycing things. Like this is it's not a ribosome problem. It's a glycine problem.
I'm confused where you're going with this.
I'm just
Trying
waiting.
to make a joke.
It's fine. Okay. Now, in this amino acid, there are actually two acidic groups in this particular chunk right here. There are two opportunities for a hydrogen to be removed. Okay. Now, any time in this particular set, if we're below a pH of a 2.34, so if we're here, both of the hydrogens that could be deprotonated are still available. They're still there. If we're here, pH greater than 9.6, both of the protons are gone. They've been removed. And at a pH of somewhere between 2.34 and 5.97, so somewhere from here to here, one of the hydrogens has been removed. Okay? Now, looking at the above structure, going from left to right, which is the first proton that appears to be removed? Yeah, the one attached to the COOH. So this proton gets removed here. As you go from through the buffer zone, and you end up with the equilibrium for the first deprotonation. And then as we travel from here to here, a secondary proton is removed. So what would be the secondary proton that's removed? The what? Yeah, that proton is removed here, and it's in its completely deprotonated state at this point. Okay? So looking at my curve, right, I can see where the initial deprotonation is taking place, somewhere in the pH range of 2 to 3-ish. And the deprotonation of the second hydrogen is taking place in the pH range somewhere between 8 and 9.5 or 10. Does that make sense? Okay, and then another example would be glutamate. And we have a larger structure here. In this case, just looking at the graph, how many deprotonation states do you think this one has? 3, because it has 3 pKa values. Okay. Now, according to the information that you've been given, which proton in the amino acid glutamate is the most acidic, that is most likely to be given up first? It appears that the top COOH, yeah? So in this buffer region here, this hydrogen is being removed first. Okay. For question number 2, it says which species in glutamate is the most prevalent at a pH of 10.42? Well, I wouldn't say OH. I would say that this, it says, because it says which species is most present. So I would say that this would be the most present species. At a pH of 10.9 or 10.42. And then lastly, what process in glutamate is predominantly taking place at a pH of 4.62? So we're talking about like this general region here. So what process is possibly taking place? It would be the second deprotonation, but you could also protonation. But you could also probably call it buffering is occurring as well. Because as you pull a proton off, you start to produce conjugate base and you have that buffer zone, right? You follow that? Okay. So that's kind of where I'm at. Any questions about that? Yes, ma'am.
How are you able to determine that the top group, the top COOH was the most acidic?
So if we look at it like this, if this is the structure before we add any base, okay? Do you follow that so far?
Yeah.
And then this would be the structure after some base is added. And then this would be the structure after some more base is added. And then this would be the final structure after after more and more base is added. Okay? So looking at the original structure, structure 1 versus structure 2, I'm looking for where the hydrogens are being removed. So from 1 to 2, the hydrogen that's being removed is the top H off the COOH. Because going to the next one, this H3, H is still present. This is the one that's absent. So that's the most acidic proton. The second most acidic proton would be this one, because that's the next one that comes off. And then the third most acidic proton would be this one. Well, hang on. Would be this one, because this one comes off third. Does that make sense?
Yeah.
Okay. And,
Any
yeah.
other way to tell, other than looking at the structures like this?
Generally speaking, in this format, no. I think that if you were given something like this, they would give you the information like that to figure that out based on the structure and the chart. They might also say to you, what would be the pH and when the first proton is pulled off, if that makes sense. Anything else? All right then.